Hello everyone, welcome to the Tim Booker channel. Wishing you a delightful listening experience. Many of you probably already know that our universe was born from the Big Bang. All matter, galaxies, life, they were all nurtured within it. But what exactly does the universe look like? How is it composed? If you've ever pondered the question of what the universe really is, you must have desired a more specific understanding. In this audio session, we're here to decipher a book titled The First 3 Minutes, exploring precisely this topic, the early universe. It's astonishing to realize that the universe, as it exists today, all hinges upon the initial 3 minutes following the Big Bang. In these brief 3 minutes, the groundwork was laid for the subsequent 13.8 billion years of cosmic history, determining the fundamental essence and shaping the ultimate fate of each of us. The author of this book is the physicist Steven Weinberg. While he might not be as famous as Hawking among the general public, in the realm of physics, his academic standing surpasses Hawking's by a significant margin. Weinberg is considered one of the greatest physicists of our time, a Nobel laureate, credited for establishing a formidable model. In the scientific community, the significance of his model extends far beyond the Nobel Prize itself. Why is this so? Well, in modern physics, there's an ultimate goal, to unify the 4 fundamental forces of nature: gravity, electromagnetism, strong nuclear force, and weak nuclear force. Weinberg can be hailed as taking the first step towards this ultimate goal by formulating the electroweak theory, demonstrating the unification of the weak nuclear force and electromagnetism, which earned him the Nobel Prize. Following Weinberg, efforts are underway to include the strong nuclear force into this unification, although this theory has yet to be conclusively finalized. Of course, if someday someone manages to incorporate gravity into this unified theory, achieving the grand unification of all 4 forces, that individual will accomplish the ultimate goal in the field of physics, likely earning a historical standing comparable to Newton and Einstein. Now that you understand Weinberg's high standing in the field of physics, let's delve into the book we're discussing today, The First 3 Minutes. It's a renowned popular science book authored by Weinberg. So, if you wish to experience the explanations of the birth of the universe from some of the best contemporary physicists, this book undoubtedly should be your first choice. Originally published in 1977, this book emerged in a period where humanity experienced a tremendous leap in understanding the cosmos. A new theory, the Big Bang theory, stepped into the limelight, becoming the widely accepted scientific explanation for the origin of the universe. This book serves as a comprehensive summary of this emerging theory, primarily focusing on the moments after the birth of the universe. The book can roughly be divided into 2 parts: historical overview of the development of the Big Bang theory and the essence of the story I'll share with you today, which revolves around the first 3 minutes after the birth of the universe. Within this book, Weinberg demonstrates his profound expertise, employing theoretical calculations akin to projecting a movie, accurately depicting the events that transpired in the first 3 minutes, or to be more precise, 3 minutes and 46 seconds, after the universe's birth. So, strictly speaking, this book should actually be titled The First 3 Minutes and 46 Seconds. However, Weinberg himself mentioned that such a title might likely deter many readers, so let's not dwell too much on the name. Now, you might be curious about why 3 minutes and 46 seconds hold such significant importance. But hold on, in the following sections, I'll walk you through Weinberg's steps as we explore the cosmic Genesis movie, uncovering the miraculous events that occurred in those initial moments. I'll break it down into 2 parts. First, what constitutes our universe and why its recipe was decided within the initial 3 minutes and 46 seconds. Second, why these specific moments not only explain the universe but also serve as the strongest support for the Big Bang theory itself. Alright, let's start by examining what the universe is composed of. In classical physics, there are mainly 2 things, matter and energy. Later, Einstein proposed the theory of relativity, and we know of its famous equation, E equals m times c squared. Here, E represents energy, and m represents mass. In essence, this equation tells us that energy and mass are essentially the same thing, they can convert into each other. For instance, in the detonation of an atomic bomb, a small portion of mass converts into energy. In a sense, you can consider matter as a densely condensed form of energy. The greater the mass, the more energy is condensed within it. Today, our universe is dominated by matter. In other words, most of the energy in the universe exists in the form of matter. We've learned in school that the mass of matter is mainly concentrated in the atomic nuclei. Atomic nuclei are primarily made up of protons and neutrons. Protons carry a positive charge, while neutrons don't have a charge. Therefore, in today's universe, the vast majority of matter consists of these two particles, protons and neutrons. If we liken our universe to a pot of soup, then protons and neutrons are the most fundamental ingredients within this soup. They constitute the main body of this cosmic soup. There are many other fundamental particles aside from protons and neutrons, but they're more like seasonings, not the primary constituents of this soup. Scientists, through observations, have determined that in today's universe, the ratio of protons to neutrons is approximately 7:1. This means that for every 7 protons, there's roughly 1 neutron. Hence, this ratio largely determines the taste of our universe. However, this taste is figurative. If this ratio were different, our universe would be entirely different, possibly affecting the existence of galaxies, solar systems, and even ourselves. But why is it 7:1? How did this ratio come about? For a long time, people didn't know why neutrons existed, and it was once a mystery. This is because, in nature, neutrons are unstable. If they exist independently, they automatically emit an electron, decaying into a proton. This process is known as beta decay. So, where did the initial neutrons come from, and how were they preserved in atomic nuclei? Why do protons and neutrons maintain a 7:1 ratio, with not all neutrons completely decaying into protons? These questions are related to the most fundamental secrets of our universe. In this book, Weinberg tells us that the answers to all these questions depend on the first 3 minutes and 46 seconds after the birth of the universe. During these 3 minutes and 46 seconds, something significant happened. According to Weinberg, the explanation is quite simple. Assuming our universe expanded from an extremely high temperature and high density state, we can answer all these preceding questions and even detail every step of this process. Let's imagine, like watching a movie, how the universe gradually evolved. In the extremely early stages of the universe's birth, it was confined to an extremely small space, almost like a tiny dot. At this time, the entire universe existed in a state of extremely high temperature and density. For instance, just 0.01 seconds after the Big Bang, the temperature of the universe might have been as high as 100 billion degrees. This is an incomprehensible concept. We know that the temperature of the Sun's surface is only 6,000 degrees. 100 billion degrees is 16 million times the temperature of the Sun's surface, a staggering high temperature. In these conditions, the matter in the universe was very different from what we know today. Firstly, atomic nuclei couldn't exist stably because the extreme heat filled the universe with various high-energy particles. Even if protons and neutrons accidentally combined to form atomic nuclei, they'd immediately be shattered under the impact, breaking into fragments. Hence, protons and neutrons were free at that time and could only exist individually, they couldn't stably bind together. Although they couldn't bind together, the high temperature of 100 billion degrees was sufficient to continuously transform protons into neutrons and vice versa. Specifically, if a proton was struck by an electron with sufficient energy, it would become a neutron, and the reverse was also true. In the initial universe after the Big Bang, it was filled with high-energy electrons, constantly bombarding all neutrons and protons. Hence, they were constantly transforming into each other, you become me, I become you. Theoretically speaking, at that time, the probability of one becoming the other was almost equal. So, the quantity of both should have been roughly equal. That was the initial recipe of our universe and the origin of the initial neutrons. Here's something to note, initially, the quantity of protons and neutrons was almost equal. So why did it later become the ratio we see today, 7:1? This is a result of the Big Bang. The key lies in this: as the universe expanded, its temperature continuously decreased. For every doubling of the universe's radius, the temperature halved. Remember, temperature is the most crucial factor influencing the ingredients of our cosmic soup. As the temperature decreased, it meant that the average energy carried by particles in the universe was decreasing. This led to a subtle change. As the universe expanded, the ratio of protons to neutrons was no longer 1-to-1. Neutrons slowly started to decrease, while protons began to increase. Why did this happen? The reason is simple: because neutrons are slightly heavier than protons, it requires slightly more energy to turn a proton into a neutron compared to turning a neutron into a proton. When the universe was at an extremely high temperature, this difference could be overlooked because the universe was filled with a large number of high-energy electrons. For these electrons, converting neutrons into protons or protons into neutrons had almost the same difficulty due to their high energy. The energy required for these two processes, although slightly different, was nearly negligible. So initially, the ratio between neutrons and protons was 1-to-1. However, as the universe's temperature decreased, the average energy of electrons gradually decreased. This is when the difference began to show. Because at this point, there wasn't enough energy. Some electrons could only convert neutrons into protons and not the other way around. Consequently, more neutrons transformed into protons, causing the proportion of protons to slowly increase. By about 14 seconds after the Big Bang, the universe's temperature had dropped from 100 billion degrees to 3 billion degrees, and the ratio of protons to neutrons had accordingly shifted to approximately 83-17, almost 5-to-1, which was significantly different from the initial 1-to-1 ratio. At this point, something important occurred. When the temperature dropped to 3 billion degrees, the mutual annihilation between electrons and positrons in the universe began on a massive scale and ceased to regenerate. In a very short time, over 99% of electrons in the universe disappeared. From then on, our protons and neutrons mostly stopped converting due to electron impacts. Does this mean that the ratio of protons and neutrons was then fixed? Unfortunately, no. As we mentioned earlier, a neutron in its free state is an unstable thing. Even without electron impacts, it would spontaneously transform into a proton through beta decay, and this process is unidirectional. It can only transform in one direction and not the other way around. In the first few seconds after the Big Bang, this effect wasn't very noticeable because each neutron took an average of about 15 minutes to decay. But now, this became a factor that needed serious consideration. Originally, there weren't many neutrons left in the universe. If they were left to decay freely, they would eventually all disappear, transforming into protons. So, why does our universe exist today? The key still lies in the temperature. As we mentioned earlier, beta decay of neutrons has a condition: it must occur in a free state. However, if a neutron can combine with a proton to form an atomic nucleus, the neutron won't decay. This brings a glimmer of hope. To preserve the remaining neutrons, they just need to settle down, that is, bind into atomic nuclei. However, things aren't that simple. As we mentioned earlier, in the early stages of the Big Bang, because of the high temperature, atomic nuclei couldn't exist stably. In other words, under high temperatures, the families composed of protons and neutrons were easily disrupted by high-energy particles, especially the simplest family unit, consisting of just one proton and one neutron. Such atomic nuclei were highly unstable and easily disintegrated. However, as anyone who has studied chemistry knows, atomic nuclei have more stable configurations, like the nucleus of helium, which comprises 2 protons and 2 neutrons. This family of 4 is highly stable and difficult to break apart. But the issue is that 2 neutrons and 2 protons can't just come together all at once, it has to happen step by step. No matter what, there must first be a stable existence of the simplest combination, 1 proton and 1 neutron. Then, other individuals can gradually join in. Thus, there exists a bottleneck here. No matter what, you must make sure that a simple combination of 1 proton and 1 neutron can exist stably before proceeding to form more stable family models. If the first step can't be achieved, then there's no point in discussing the rest. In summary, to save the remaining neutrons, we must await a specific temperature in the universe, where the simplest atomic nucleus, comprising 1 proton and 1 neutron, can stably exist. If the universe can reach this temperature before all the neutrons decay into protons, then we can save the remaining neutrons by binding them into atomic nuclei. Conversely, if the universe's temperature decreases too slowly, we'll just watch helplessly as all the neutrons decay into protons. We know that protons form the nuclei of hydrogen atoms. In other words, if all the neutrons decay, then apart from hydrogen, most other chemical elements in the universe won't exist anymore. So, what's this temperature? Weinberg tells us it's about 900 million degrees. In other words, we must patiently wait until the universe's temperature drops to 900 million degrees for stable atomic nuclei to appear. And when will the universe's temperature drop to 900 million degrees? Weinberg, through calculations, provides an answer. You probably guessed it, that magical number we've mentioned repeatedly, 3 minutes and 46 seconds. Alright, let's see what happened at that moment, 3 minutes and 46 seconds after the Big Bang. Firstly, the universe's temperature had dropped to 900 million degrees, enabling the initial formation of a stable atomic nucleus with 1 proton and 1 neutron. Soon, a new proton and a new neutron joined. Building upon this, they continued to combine, forming a more stable 4-person combination, the nucleus of helium. The key is that we were incredibly fortunate. At 3 minutes and 46 seconds after the Big Bang, all the neutrons in the universe hadn't decayed yet. Through calculations, we can conclude that about 13% of the neutrons remained in the universe at that critical moment. Therefore, during that decisive 3 minutes and 46 seconds, all the remaining neutrons in the universe were bound into atomic nuclei, where they wouldn't decay. Thus, these neutrons were preserved for a long time. From that moment onward, the ratio of protons to neutrons in the universe didn't undergo significant changes. In other words, the formula of our universe was then fixed. Over the next 13.8 billion years, the universe continued to evolve based on these materials, eventually forming what we see today, stars filling the sky, the radiance of the sun and moon, the vast mountains and rivers, the rise and fall of rulers and emperors. Essentially, everything we see today and know today is mostly composed of these particles. It can be said that the fate of the entire world was basically decided at this critical moment we've discussed. This concludes our discussion on why the formula of the universe was determined in the first 3 minutes and 46 seconds. Next, let's talk about the second point, why this conclusion is crucial to the Big Bang theory itself. Previously, scientists knew that the ratio of protons to neutrons in the universe was roughly 7-to-1 but didn't understand why. However, the Big Bang theory can provide a detailed answer. Through calculations, we've concluded that around 3 minutes and 46 seconds after the Big Bang, the universe inevitably formed helium nuclei, and at that moment, all the neutrons would have been bound into atomic nuclei. Similarly, through calculations, we can ascertain that about 13% of neutrons were inevitably left in the universe at that time. In other words, roughly 87% were protons. Dividing 87 by 13 gives us approximately 7-to-1, perfectly answering the earlier question. Moreover, we can address another famous issue called elemental abundance. Elemental abundance refers to the relative content of elements in the universe. Scientists long knew that our universe is primarily composed of hydrogen and helium in a ratio of about 3-to-1. But why? There wasn't a clear answer until the Big Bang theory offered a simple inference from the ratio of protons to neutrons. At around 3 minutes and 46 seconds, the ratio of protons to neutrons was 7-to-1, and nearly all neutrons had formed helium nuclei. This inevitably led to the universe's hydrogen to helium ratio being about 3-to-1. You might ask why only helium nuclei were formed at that time and not more complex ones. Helium nuclei were the easiest to form. Though theoretically, stable families with more members are possible, including nuclei containing neutrons, nature is miraculous. Wanting to increase the number either requires adding another member to the family of 4 or merging 2 families of 4. Unfortunately, whether it's a 5-member or 8-member family, it's not stable. Thus, this merging couldn't naturally happen. Physics demonstrates that after the initial 3 minutes, almost all neutrons ultimately entered helium nuclei, the family of 4. To form larger families, we must wait until much later, till the time when stars begin to burn. This proves that our universe necessarily comprises roughly 75% hydrogen and 25% helium, perfectly aligning with observations. Don't underestimate this, it's significant. This result demonstrates that the Big Bang theory isn't just empty talk but a scientific theory capable of precise predictions and testing. Apart from elemental abundance, the Big Bang theory also predicted the famous cosmic microwave background radiation. It tells us that 380,000 years after the universe's birth, as the temperature continued to drop, remaining electrons combined with atomic nuclei, forming complete atoms. With no free electrons obstructing them, light for the first time traversed the transparent universe, leaving behind the cosmic microwave background radiation at a temperature of around 3 Kelvin. In 1964, two American physicists, Penzias and Wilson, accidentally discovered this radiation, earning them the Nobel Prize. The cosmic microwave background radiation stands as one of the 20th century's most important scientific discoveries and has become a legendary moment in scientific history. The fascinating part is that such an essential discovery was purely accidental. Initially, these two were just trying to create a highly sensitive antenna, never expecting to stumble upon an echo from the universe's birth. In this book, Weinberg also shares his perspective. He believes that even the physicists proposing the Big Bang theory underestimated the power of science. They couldn't have imagined that a theory based purely on mathematics, a model deduced solely on paper, could accurately describe our universe and align so well with observations. It's almost unbelievable that through pure theoretical calculation, we can precisely recreate the evolution of the universe in its initial 3 minutes and even accurately predict the composition of today's universe. It's an incredibly unimaginable feat. Perhaps this book also gives us another revelation: no matter how vast and distant the universe seems, it's still understandable and predictable through scientific methods. Starting from a few simple assumptions, we can use physics theories to meticulously calculate the entire process of the universe's birth. However, this book was first published in 1977, over 40 years ago. It describes the so-called standard Big Bang model. Today, our understanding of the universe's essence and origins has deepened. We've discovered that ordinary matter in the universe is just a small fraction. Besides, there exists mysterious dark matter and dark energy. We realized that before the standard Big Bang stage, the universe underwent a more intense explosion. We've proposed more advanced theories like the M-theory, Higgs mechanism, symmetry breaking, and so forth. Though these terms might seem like gibberish to lay people, someday, these theories might also be proven. Then, our understanding of the universe will significantly advance again. So, let's remember, never underestimate the power of science. Sure, let's summarize today's audio content. How did our universe come to be? Why is it the way it is today? Now we know that to a large extent, it all depends on what happened within 3 minutes and 46 seconds after the Big Bang. At this critical juncture, the fundamental recipe of cosmic matter, the ratio of protons to neutrons, was established, thus determining the quantity of hydrogen and helium and ultimately shaping the direction of the universe's evolution. Weinberg demonstrated that through the Big Bang theory, we can intricately describe every step of this process and predict the proportional compositions quite accurately. All this just requires a few simple assumptions. So, in a way, the initial 3 minutes not only reveal the dawn of the cosmos but also showcase the significance of science itself. From Weinberg's portrayal, we not only witness the magnificence of the universe and the wonders of nature but also can't help but marvel at the grandeur of human intellect. With the power of science, we, on a seemingly insignificant little planet at the edge of a galaxy, after 13.8 billion years, can use nothing but paper and pen to glimpse the dawn of the universe's creation. Is there anything more incredible than this? That concludes the essence of this book. Congratulations on completing another book. Thank you all for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with friends. Let's combine wisdom and practice to achieve our financial goals and create a better future together. Thank you, goodbye.